All right. Welcome back. So this is going to be our first actual content lesson. Instead of just talking about stuff having to do with the course, we're actually going to get into some physics now. So if you've ever taken a biology course or a chemistry course, you've probably seen units, unit conversions, and the whole significant figures thing. Some of you probably seen it in high school. It's been a minute since I've been in high school, so I can't remember exactly how this is covered. So hopefully this is a bit of a refresher, which would be nice to make sure we're all on the same page. All right, so let's get started. I'm trying using notating on my iPad so you guys can see what I'm doing. Hopefully this works out. Yeah, so 1.1, units, conversions, and sig figs. So traditionally, this is worth saying. Most students, when you begin a physics course, a lot of students, I myself included, when I was doing this, I found the topic of units and conversions very tedious and boring. But I did find later on in my career, having a good knowledge of just unit conversions and dimensional analysis was actually really helpful in my job. You can, perform a sanity check on your work all the time just from doing dimensional analysis. And that's just essentially making sure you wind up with the correct units at the end of the problem. So don't think it's boring and tedious, even though it may feel like it. It's very helpful to be really good at this. So again, understanding the natural world and the built environment. So I imagine a lot of you are going to be engineers, so especially the built environment, that's going to be important in understanding all these things that you're measuring when you're building quote unquote things. Even if you all want to go into something more, physics-based or chemistry-based, you got experimental measurements going on. Yeah, all that's important. You need to know how to do this dimensional analysis. It's also important to understand that there are different systems, different ways that you can measure the exact same thing. So you need to make sure you understand how different systems of measurement are connected. I always like to think about these 4 examples when I'm trying to convince someone that these types of measurements and these types of calculations are in fact important. So we've got 4 different examples of measurements going wrong in essentially 4 different eras. So let's get started with this first one, going all the way back to like Christopher Columbus's voyage. And if you see these 4 and you're interested, there's actually a whole book called Humble Pie. This is where I got these examples. It's a whole book about when math goes wrong in the real world, just like the title says down here. So these are worth noting, and we'll talk about each one in a little bit of detail. So as far as Christopher Columbus, so his big issue is that he calculated the distance from Spain to Asia because he thought he was going to circumnavigate the world. He calculated it in Italian miles instead of Arab miles. So the distance he calculated was much shorter than what it was actually going to be. Luckily, he actually ran into North America. So had he not came over to the Americas, he would have been going much further than what he actually calculated. So it was a happy accident that he found the land that he did. The Vasa, which was a Swedish warship, the builders building it actually used 2 different systems of measurement. One side was built with, the Swedish feet ruler, and the other side, the construction workers were using the Amsterdam feet ruler. So they're really close if you just hold them up, but when you have a small difference and you do that for, a lot of measurements, it actually caused the whole ship to be lopsided, and a strong gust of wind came and sank it like immediately. Another interesting one is the Gimli glider. So this Air Canada flight, it was scheduled to fly from Montreal to Edmonton, and it was going to stop in Ottawa. So the ground maintenance in Montreal did a fuel calculation to see how much needed to be, put back in the plane so it can make it. Well, they used pounds instead of kilograms. So that was the first issue. However, even though it was drastically underfueled, it still had enough to make it to Ottawa in that stop. What's really interesting is that same thing happened again right here. Same error happened on the way to Edmonton. So they screwed up twice, but it only actually ran out of fuel on that second leg of the trip. So it actually had to come in for a gliding landing in an abandoned military base in the town of Gimli. That's why this aircraft is known as the Gimli glider. It actually, I think it flew for 25 years after this. They actually repaired it. So these are so far 3 examples of where people could have died just because units were incorrect. So even though it feels like they're tedious when you do it, clearly it's important. So the last example, the Mars Climate Orbiter. So NASA launched the Mars Climate Orbiter, and it's supposed to essentially graze the upper atmosphere of Mars and collect some data. But there was a unit conversion. So this instrument was recording thrust in pounds, so like the imperial units of thrust, but it needed to be in newtons, and we'll talk about newtons later. That's essentially the metric version of pounds. So we had a newtons versus pounds issue, and that actually caused the spacecraft over. You can imagine if this thing keeps calculating thrust, even though if the numbers aren't that different, over time with the wrong units, it gets very, very bad. The errors just compound. So what happened here is the spacecraft was essentially much too close to Mars, and it burned up in the atmosphere. Okay, so that being said, there we go. So that being said, there's several different types of units of measurement out there. We talked about like the Italian mile, the Arab mile, the Amsterdam ruler, then like imperial versus metric. What we're going to use in this course and what's common pretty much globally in all the sciences is the metric system. So that actually comes from its French title. I'm not even going to try it because my French is very bad. But essentially the International System of Units, so it's abbreviated as SI units, which is why I've got it in yellow there. So with the SI units, there's essentially 7 base units in this system. So that means like just fundamental things that you can measure. You can break them down to anything else. The 3 we're going to deal with right now, and we'll get to the other ones later, are essentially time, length, and mass. Here's the 7 base units here in this chart. You can read the description if you'd like, but we're just going to deal with the first 3. So we can measure times, we can measure meters, so distances, we can measure times, distances, and then the mass of something. Now let's talk about these 3 units of measure. So the unit of time, the fundamental measurement, is the second, and all of these base units, they have really technical definitions because you want to make sure everyone on the whole planet, ideally in the whole universe, is using the same definition for the second, for a length, for a mass. So here, the second is essentially defined as the time required for a certain number of oscillations of a radio wave absorbed by a cesium atom. So here you see this cesium atom, and like all atoms, it will absorb and emit photons. So a photon is just both a wave and a particle. It can come into an atom and excite an atom, but when an atom decays, it'll shoot one out. So here, this wavelength, this is our photon, and photons have different frequencies. That's like, visible light, that has a certain range of frequencies we can see. X-rays, high frequency, radio waves, low frequency. They're all photons. They're all acting like particles and waves. So essentially just a very specific wavelength from a cesium atom after so many oscillations. Once we have our stopwatch and we click start, as soon as that number of oscillations happens and we stop it, we'll be at exactly 1 second. Now the meter is actually went through several different definitions of time, so has the second. But the meter, the last definition, was actually based on the speed of light in a vacuum. And it's important to note that this is in a vacuum, because the speed of light actually changes a little bit depending on if it's going through water, if it's going through the atmosphere, or if it's going in a complete vacuum like in space. So essentially, a light particle, so another photon, you can imagine any photon, this isn't just for a specific wavelength, but any photon, as it's propagating along, once it goes 1 meter, well, that happens in like 1/300,000th of a second. I'm sorry, no, that's not thousandths, 1/3 millionth of a second. I'm always used to writing that number in scientific notation, which we'll talk about later. So essentially, in just a tiny fraction of a second, a light wave will go 1 meter. Now, the kilogram is a little interesting. So the kilogram is actually based on a manufactured object. So cesium is naturally occurring, photons are naturally occurring, but now how we define the kilogram, that is based on this platinum iridium cylinder, which is stored in Paris. So there's 3 or 4 of them, and they're distributed, like, I think the US has one at NIST, the National Institute of Standards and Technology. I guess maybe London has one. I'm not sure where the second one is, but there's one in Paris. What's really weird and really freaky is they've taken so many precautions to preserve the kilogram, but it's still losing mass. And last I checked, no one's really sure why it's actually slowly losing mass. Now, the mass that it's losing is very tiny, but it is measurable. So that's really interesting, and it has some implications, because the way we define mass is slowly over time getting smaller, which is a little creepy. Okay, so we talked about these base units, but what if we're talking about things that are much smaller or much larger than just the standard unit? You know, if we wanted to talk about the length or the distance from the East Coast to the West Coast, well, we don't want to say that in meters because it's going to be a huge number. So if we're talking about things that are much smaller or larger, we can actually attach prefixes to these numbers. And the prefixes are just to denote powers of 10. Okay, for example, if we wanted to talk about the circumference of the Earth, which is roughly 40 million meters, well, that would be a lot of zeros after 40 if we wanted to write it out over and over and over. So we can actually attribute just a large, a prefix for this large number. So if we say 1 kilometer, well, that kilo means 1,000. So now we take our 40 million meters and chunk it up into bits of 1,000 instead of using all 40 million of them. And then 1,000, you'll notice if we move our decimal place until we get to the 1, so if we go well, we've moved it to the left 3 decimal places, so we can actually rewrite it as 1 times 10 to the third. If you put that in your calculator, 1 times 10 to the third, it'll be 1,000. So this over here on the right is scientific notation. I'm going to abbreviate. Scientific notation, and then that's just a fancy way of writing these numbers with long zeros as powers of 10. Oh, hold on, I'm having trouble going to the next thing. Sorry about that. All right, so the megameter, I suppose you could say megameter, I'm not sure. So that's essentially 1 million meters. So now we're going to take our 40 million and chunk it up into millions instead of thousands. Same thing, scientific notation is on the right. You'll notice we can move our decimal place times 6, and that's going to give us that power up there, that power to the 6th. Now, well, let's do that. Let's actually take the radius of the Earth, and we'll chunk it up by the 1,000. So 40 million divided by 1,000, well, that's just going to be 40,000 kilometers. So that's the radius. Did I say, nope, that's the circumference of the Earth. So I've already messed up. This needs to be circumference of the Earth is, what did I say, 40,000 kilometers. Same thing here. Circumference. So the circumference of the Earth would be 40 megameters. So you see how we're just chunking things up? So essentially the exponent indicates the number of decimal places that are essentially absorbed by the prefix. So when you move that decimal over, you're essentially absorbing those numbers, and that's where that prefix is going to step in. So there's actually a lot of prefixes. Here's a list. I don't think you'll need to use all of these, at least not in the Physics 1 course, maybe in Physics 2. But we notice we go from -15 as our exponent, so something super tiny, all the way down to tera, which is huge numbers. All right, so let's take this arbitrary example of 1,247 meters. Well, we could write that as kilometers. You'll notice that it just becomes a decimal, right? Because we're going to not a whole lot of meters, and then we're writing it in terms of thousands. So it's 1.27 or 247 kilometers. Same thing if we wanted to write it in megameters. I don't know why we would, because that just makes a really gross decimal at the end. Typically, you'll want to lump these in like groups of 1 or 3 in the front there. So the bottom one isn't really practical. You wouldn't like write this if you were doing a technical report. You wouldn't write it in megometers just because it makes it look weird with all the decimal places. But the point here is you could if you wanted to. One more thing to note. So when you go from a big number and you collapse it down, you move the decimal place to the left. If you have a small number and you want to write it as something bigger, like, if you have not a lot of meters, maybe you want to write it as millimeters, you move the decimal to the right and then apply the exponent on your power of 10. So as far as quantities given prefix units, if you're going to give them, yes, if you are given them with prefix units, you need to convert those to base SI units. This is very important. So if you are given something in a problem or in the real world in kilometers, but you're going to do a fundamental physics calculation, all of the fundamental physics calculations are generally set up for base units. So make sure you're always using base units when you do these problems. Also, if you have other systems of measurement mixed in there, maybe some of your measurements are taken in like feet and inches, but you're doing your calculations in meters in the SI system, make sure you convert everything to the SI system and then do the math. Otherwise, you're going to have problems. You're going to have the Mars orbiter issue all over again. So let's do just a couple more examples. So given that 1 mile is 1.609 kilometers, okay, given this fact, okay, convert 1,247 meters to miles. Okay, so here's the actual problem. It's important to note. Okay, so here's the actual problem, but we're given some extra information. So a lot of times, especially when I was learning physics and I'd read problems, I would always get lost in the sauce, so to speak. That's what one of my old roommates in college used to say. Yeah, I would get lost in all the information that I was given, and it'd be hard for me to pick out what the actual question was. So sometimes you need to read these backwards. So we know what the question is. We're converting 1,247 meters to miles. However, we need to use this fact over here. 1 mile equals 1.609 kilometers. Now, there's two things going on here that we need to make note of. Okay, so there's two relationships. We have meters, kilometers, and there's also kilometers, miles, right? Because this is going from the SI, SI to imperial, right? So we're not just staying in the same system of measurement. We actually have this transition. So we've got multiple relationships we're dealing with here. So the first relationship is the kilometers to meters, okay? Second relationship is the 1 mile equals 1.609 kilometers, okay? You'll notice the first relationship is the metric system and stays in the metric system. Relationship 2 is our bridge between the two. Okay, so for this first one, what we can do is take this simple mathematical statement is essentially an equation. One thing equals something else. Now, if we divide both sides of this equation by 1,000, look at what happens to the 1,000 meters. Well, that's just 1. So really, 1 kilometer divided by 1,000 meters just equals 1. That's super basic, right? We can do the same thing with this other relationship. So we can take 1 mile and divide the both sides essentially by 1.609 kilometers. And what that's going to do for us is essentially give us a ratio equal to 1. So this, when you have one set of units equals another thing, you can always set up this ratio. And when you do, you're essentially looking at a really weird way of writing 1. 1 mile divided by 1.609 kilometers is just 1. So you'll notice, since we have 1, we can take whatever we want and multiply it by 1, right? And it doesn't change anything because multiplication by 1 doesn't do anything. So if we have a foreign quantity, so here this foreign quantity is 1,247 meters. We don't like that. We want to change it to miles. So we can take that chunk of meters and we can multiply it by 1 all day long. It doesn't change it, right? So let's multiply this foreign quantity. So notice we're just multiplying by 1 over and over, right? The ratio here is just equal to 1. The ratio after that is just equal to 1. Now, so we have our original value, our foreign value, and then we're literally just multiplying by 1 twice. We have 1, 1. Now, notice what happens with the units. I've marked it here in color. The meters, you have a meter on top and a meter on the bottom. They cancel, just like in algebra. Same thing with the kilometers. You have 1 on top and 1 on the bottom. They cancel out, just like in algebra. So you'll notice what's left. We have miles left. That's exactly what we wanted. We wanted the units to come out of this at the end to be miles. And you'll notice once all those units cancel out, it's just a multiplication problem. And then the units on this big multiplication problem, because they're the only thing left over, is miles. Okay. There we go. And here's the note. Units work just like algebraic quantities. So notice like there's an a in the numerator and an a in the denominator, so they'll cancel out. Now, the way I normally wrote this and the way I learned way back in the day in high school is essentially called fence post notation. And this is essentially where you sort of chunk it up with like you got this one long bar, and then you just draw your vertical lines to chunk up each individual piece. Once you write all of your conversion factors in there, so you'll notice it's still just a multiplication by 1 and a multiplication by 1. Once you write all your conversion factors in there and then you cancel, you'll notice the meters cancel, the kilometers cancel, and you're left with miles. The fence post notation is a little easier to read because once you get everything in there, you just multiply across the top and multiply across the bottom and then just keep simplifying. So you'll notice miles still lives through that process. And then you'll get the answer here. So 1,247 meters is roughly 0.78 miles. I think I do have one problem in the problem set where essentially you need to do a ratio. So if you had like, if you had a rate, so maybe a speed, maybe 1,247 meters per 1 second, you could even do the same thing and mix in seconds and minutes or seconds and hours, whatever you needed. So as long as you're multiplying by 1 each time and your units are canceling the way they should, you can actually do 2 problems at once. You can do one conversion in this numerator up here. And then you can also, if it's a rate problem like miles per hour, you can also convert the bottom in the same fence post notation. It gets a little tricky, so it takes a little practice. But this does, you can see right here, it's not a pretty answer at the end, but this is an important question that we need to ask, and that is, how many decimal places should we include? Because here there's like, I don't know, 10 decimal places, but then you'll notice I've written it's approximately equal to 0.78. So that's going to bring us to significant figures. It is very important in science and engineering to not provide a bunch of extra digits. If you're providing digits down to the 10,000th place, but you don't have any machinery that can measure that, you're reporting values that are way more accurate than they should be. So you don't want to lie about your accuracy and how accurate you can be in your measurements. So that's why we have to consider these significant figures. And that's just essentially the digits that are reliably known. So the appropriate number of significant figures for a calculation is basically determined by the initial data that's been provided. Here are some rules. I suggest you pause and read these thoroughly. They'll be very helpful. But essentially, the things to remember, not all non-zeros are always significant. Now, there's some zeros that are significant, some zeros that aren't. So you can see here in the second part, interior zeros. So if they're a part of the number, like this 402 over here, or this zero up here in this decimal, well, clearly they're significant because they're part of, you know, that piece of number. However, leading zeros, so just all the nothingness until you get to a significant figure, those don't matter. So you can see like this point, what, 0.0000002, all those leading zeros, they're not significant. Trailing zeros can or cannot be significant. So if there essentially is a decimal point present in the number, then they could be significant. If there's no decimal point, then they are not significant. And then exact unit conversions, essentially you don't have to worry about those significant figures. You're going to assume that they're exact. So overall, if you're multiplying or dividing, you go with the least precisely known number in the calculation as far as sig figs. So multiplication and division, you're going by the sig figs of the data provided. With addition and subtraction, you're going to go by the decimal places of the number of the numbers provided. When you're doing intermediate calculations, though, you can keep all the units you'd like. As long, what we're looking for here is just reporting your final answer appropriately. So here's just a few examples. You can see here in the column on the left, each one of these, the first two, 5 significant figures. See that 0 there at the decimal place? So what this is saying is, okay, so we measured this thing that's exactly 5,010. However, if we needed to, we could measure to that first decimal place. It just happens to be like the exact number 5,010. That's why that's there. Just letting you know that accuracy is there. It just so happens that we didn't measure a number that needed to be in that decimal place. On down here, you'll notice that in C, these don't matter. They're leading, so those are not significant. So this part, number C here, just has 4 significant figures. Now with scientific notation, the way it's written is you always have a single number out front, but this first part, this first chunk that's multiplied by the power of 10, that's going to tell you how many sig figs there are. So here you can see there are 4 sig figs. Now over here on the right-hand side, you see how we're adding and subtracting, so we go by the number of decimal places. Well, there's no decimal places on 5,032, so we know we need to truncate in the answer. Same thing here, except we're multiplying, so we need to examine our data given, 57 or 7.368. Well, 57 is only 2 sig figs. Okay, so the 57 is going to dictate that we only have 2 sig figs in our answer. Then same thing down here in C, we've got 4 sig figs in this number. That's the least precisely known, so that's going to dictate what happens over here. So that's the crash course in significant figures. So now let's put all of this together in a example problem. So Alice and Bob recently purchased a small rectangular piece of property, and they would like to know its area and perimeter. So Alice quickly measures one side to be 32 feet. So notice it says quickly measures, and then there's no precise, like there's no inches to follow. She just says, oh, it's about 32 feet. Now, Bob, on the other hand, measures with more care, and he determined his side to be 18.1 meters. So clearly we've got some issues because we have two different types of accuracy. We've got two different systems of measurement. So we need to be mindful of this difference in measurement, and we also need to be mindful of significant figures. So first, let's determine the area of the property. So what we can do first is convert Alice's measurement from 32 feet to meters. Okay, so here, well, we can keep multiplying by 1 until we get the units we want. There's 12 inches in 1 foot, so we know that's a multiplication by 1. You'll notice that feet are on the bottom, so they will cancel out with the 32 feet. But now we're left with inches, because these cancel out. Okay, well now we need to get rid of the inches. Well, there's 2.54 centimeters in an inch. Okay, so we can again multiply by 1. Okay, where will the inches go? Now we still have to deal with the centimeters. Again, we will multiply by 1. Okay, and then that's going to convert our centimeters to meters. Okay, that's what's coming out of this process, which is exactly what we wanted. Now, once we just do this multiplication, turns out Alice's side is 9.7536 meters. Okay, that's quite a bit of decimal places, but remember, these are all unit conversions, so we're going to call this as an exact number. Okay, sorry, I write in cursive sometimes, it's just a little faster, so I apologize. I try to write in print during lectures, but it doesn't always happen. All right, now we're good to go. We've just moved everything into the correct system of measurement. So we'll take Alice's value A and Bob's value B, multiply them together. You'll notice that we get quite a hefty number with lots of decimal places. But remember Alice, 2 sig figs? So that means we can say the area is roughly 180 meters squared. Now, yes, okay, so remember, these values work, or these units, the meters, they work just like letters. You have meters times meter, m times n. Well, that's just m squared, just like in algebra when you're using letters and variables in your math problems. So don't forget, if you do have a situation where you have units multiplied together, if it's the same thing like meters and meters, then it'll be meters squared. Now let's just determine the perimeter of the property real quick. So essentially that's just 2 times Alice's side and 2 times Bob's side, since it is a rectangle. You'll notice that again we get a lot of decimal places, but 2 sig figs, so the perimeter is roughly 56 meters. Okay, let's look at just a quick summary of what we talked about. This will be essentially the basics of what you'll need to finish your first problem set. I've posted some additional videos about these topics, so feel free to watch those. You should be able to find a chunk of this textbook, the Physics for Scientists and Engineers by Randall Knight. I've posted a few pages out of that you might find helpful. So go ahead and review all of that, and let me know if you have any questions about that first problem set, but it's going to cover essentially what's here. So we have the intro to units, the importance of units. So we went through several of those issues where units turned out to be a big problem. We've talked about prefixes, so how you can write really small numbers or really large numbers. We've talked about unit conversions. We also talked about the SI system and its base units and the history of those, where they came from. Just for your broad physics history knowledge, those 3 base SI units that we're going to use in this course often, those actually are based on real physical things you can measure, which I think is pretty cool that we have a whole system of measurement based on things that are reproducible, so we can never not know what a second is. We can never not know what a meter is, because we've based them on things that happen consistently in nature. Now, because the kilogram is slowly decaying, that might cause issues, so perhaps we need to come up with a different way to define it. And then the last thing is just significant figures. So that's all for this lecture. Feel free to go back and rewatch anything, pause, take notes. You should also be able to find PDFs of all these PowerPoints. So if you want to print them out, you're more than welcome to and make notes on those. So I will see you guys next time.